Okay, good morning. Good morning, everybody. Welcome to the tutorial on Riemannian geometry for scientific visualization. So what will we talk about? The motivation for doing this is basically that Riemannian geometry is a very important part of differential geometry, but it's not so often used in visualization applications. Unlike differential topology, for example, where there are a lot of applications using topological features for feature analysis and so on. But Riemannian geometry, I think, is a bit underrepresented in the visualization literature. And so we would like to help a little bit to rectify this and introduce more the importance of Riemannian geometry for scientific visualization. It's also not only about Riemannian manifolds with a Riemannian metric, as we'll see, but it's in general about, let's say, modern differential geometry with modern constructs like differential forms, coordinate-free approaches, tensor bundles, vector bundles, and so on. So what we'll do is we'll introduce the most important basic concepts and illustrate some example applications for visualization with the main goal in some sense is probably gaining more insight, like what different constructs in visualization actually mean and what different constructions or different variants would change. But also there are some computational advantages. For example, if you compute geophysical fluid flow on the surface of the Earth, you can either do that in 3D space with 3 components per vector or in 2D space on the sphere with 2 components per vector. And especially if you compute a large vector field, of course, it's beneficial to do that with 2 components instead of 3 components and so on. So the fundamental question is kind of what's the domain or the space of scientific data? Where do these data actually live? And often this is kind of ignored to some extent, so it's usually Euclidean space R2 or R3, but in general the space where this data live is a topological or a smooth manifold. And so we want to look at what this entails. And actually there's a lot of influence on constructs that everybody takes as given, like derivatives, for example, but the construction of many derivatives depends on what the actual definition of the space is. And this Riemannian metric is an important part of this definition. So the meaning of having a constant vector field, for example, or a parallel vector field, or even a flat space or a curved space, for example, depend on all these constructions. And then if you ask, are 2 spaces the same, the metric is important, or especially if you ask, are 2 tensor fields or 2 vector fields the same? All of this is very important to use this fundamental concept of a Riemannian metric on a manifold. So some examples of what we'll look at later that corresponds to this is what's called connections and covariant derivatives. So basically also the construction of a velocity gradient tensor that's very common in continuum mechanics and flow visualization, of course. Also is already a covariant derivative if you look at it in a more general setting, and a covariant derivative is not just partial derivatives. Okay, so here is the team that developed this tutorial. I would especially like to refer you to the tutorial web page. At this URL here, you can download tutorial notes, so we won't have time to cover all of the details very, very much in detail, so I refer you to the tutorial notes. That's like a 90-page PDF file now. And then we will present, Peter and I, like an overview, basically of all of these concepts, but then please look at the tutorial notes for more details. There is also Tom Teusel. He's not here as a speaker, but he's online, so if you have questions, you can post them on Slido or Discord. He will try to answer them also during the tutorial, because we will try to cover some questions at the end of each session, but we won't have time to answer a lot of questions. So you can post them online and Tom will try to answer them. Okay, so a rough schedule. We have like 2 sessions before the break and after the break. And so there's 2 parts to each session. So the first part I will present, and then Peter will present the second part. And after the break, we do it the opposite way. So basically there are more basic concepts before the break and a little bit more advanced concepts after the break. And especially we'll show more applications also after the break. So the first part we'll use to cover important basics. So before we dive into some actual details, let me give you an overview, like a quick preview of the most important concepts that we'll try to cover. So of course we are talking about Riemannian manifolds. So manifold is basically an n-dimensional space where every neighborhood of every point can be represented by an n-dimensional construction. And in addition to just the topological manifold where distances and so on are not important or not even defined, if we want to also compute distances and angles and so on, we need a Riemannian metric. The Riemannian metric is a tensor field, a second order tensor field that's given on this manifold. That's often denoted by G, as shown here. And basically this is a function, so a bilinear function that takes two vectors as an input and gives the scalar product as an output. So basically that's very well known if you just think about the dot product, for example, but actually this metric works in general in a coordinate-free sense, whereas the usual dot product equation would assume Cartesian coordinates, for example. So basically it's about an inner product. We have a tangent space at every point on a manifold, and in this tangent space we have an inner product defined, but then because we have a manifold with many tangent spaces, so every point has its own tangent space, we need this inner product to be defined like a function that varies smoothly over this manifold. If we write this more in tensor notation, you would write it like this. So you can refer it to components, but you can also just see it geometrically like this. So then the inner product would correspond to this geometric meaning. So as you can notice here, there are no coordinates here. I mean, if you look at this often, you think immediately about coordinates, but it's important to realize that there are no coordinates here. It's just the length of two vectors and the cosine of the angle between the two vectors. There are no coordinate components. If you want to do it in coordinates components, you can do that, but then you have to refer it to a particular coordinate system that we'll talk about. Then refer to this coordinate system. We have coordinate components of the metric tensor itself, and this would be the basis, in this case using the tensor product, because it's a second order tensor. So we'll look at that in detail. So this has many applications. It sounds quite simple, I guess. We have an inner product, like a dot product, and so on. But from that, you can immediately derive what's called a connection. So we'll specifically look at metric connections, connections that are compatible with metric. The most important one is the Levi-Civita connection that's uniquely defined as soon as the metric is given. And from that, we can scalar fields, which is a zeroth order tensor. But if you have a first order tensor, like a vector field or a higher order tensors, directional derivatives basically have to be defined by defining a connection. And if you use a metric connection, they're defined by defining the metric. So often you would just see that it is implicitly given, but in the general setting, it's not implicitly given. It has to be defined. That also entails things like parallel transport. How do you do a parallel transport of vectors? What does it even mean to be parallel? And an important application would be geodesics, for example, where the tangent vector of a curve is parallel transported along the curve itself. Of course, curvature is then also important, but we'll not go into the details of curvature in this tutorial. What we'll be also using, that's very convenient, that's very common in tensor computations, especially in general relativity and so on, it's famous, it was called the Einstein summation convention. Basically, it's just removing all the sum sign that are kind of implicitly clear anyway. So this is completely equivalent, these two parts here. It just means that we sum over all the indices. The index would run from the first index to the number of dimensions that the manifold has. So if it's a two-dimensional manifold, there are two indices. We have this definition, which is implicitly a sum over all the indices. So we pair basically vector components in this case with a basis of vectors. So you have to read it like this, but then it's usually never written like this because it's just too verbose. We can also do this with multiple indices. In the metric tensor is already an important example. So you have this given geometrically here, but if you want to expand it in components, you have the components here. And then basically the components of the metric tensor are multiplied by the components of the vectors. But then this means this sum here, but usually you don't write this sum. So you have to parse it like this. This takes a bit of getting used to, but after that it's actually very, very convenient. Sometimes it's a bit tricky to track the indices, but in total it makes all the expressions much more compact. So Peter will talk more in the next. The dual space that we'll look at later, so there are vectors, and the dual space to the vectors called covectors are one forms. And if a tensor takes vector arguments, it's covariant, and if a tensor takes one form arguments, it's contravariant. A bit of getting used to, I guess. Then there can be tensors of mixed variance, so basically taking, for example, one vector and one form as an input, and a linear map that maps a vector to a map vector in linear algebra would in tensor calculus already be a tensor of mixed variance effect. Then there are differential forms, which is just a special kind of tensor. It's basically covariant tensors that are antisymmetric in every argument. Antisymmetric just means that if you switch the order of two arguments, the sign flips. So here at the bottom, there are some examples. So this would be one forms, df, dxi, like this is like a gradient, one form equivalent to the gradient. This is a coordinate differential. This would be the metric tensor that we already saw a little bit. And this would be what's in flow visualization, continuum mechanics called the velocity gradient tensor, which is a map from a vector to a vector. But if you write it as a tensor, it's a tensor as a mixed variance. So it takes one vector and one form as an argument. As we said, it's all very related to taking derivatives and how derivatives actually work. So these D symbols here would be what's called the exterior derivative of differential forms, and this nabla symbol here is what's called the covariant derivative, which will be very important later on. So a simple example is the gradient of a scalar field. I guess everybody knows that to some extent, but usually you would see that as a vector nabla f, for example, if the scalar field is called f. But the more primary notion is actually not the vector itself, but the differential one form that's dual to it, because this is always defined, and the nabla f is not always defined. And also, if you look at the equation components, like df, this is a directional derivative operator, basically that takes a direction and gives the derivative of this scalar field that's given in that direction. If you expand this in components, it always has just partial derivatives like this, so it's always the same equation. Why do I emphasize this? Because if you look at nabla f at here, it's not always the same equation, because unfortunately the equation depends on the coordinate system that's given. So in Cartesian coordinates, it's very simple, but even just in polar coordinates, it's already a bit more complicated. So I think the fundamental problem is a little bit that the equation changes depending on the coordinate system. If you do that with the dual notion of a one form, this problem doesn't exist. So basically you can convert between the two by this symbol here, that means it's raising a one form to a vector, so we'll talk about that later. But basically this df is always defined, but for this vector to be defined, you need the metric. I mean, if you have a Riemannian manifold, you have the metric, so you can convert between the two, but still it's in many applications much easier to just use the differential df instead of the actual gradient vector. It's even worse than just having different equations. So here you see there's no scalar multiplier here to the partial derivatives. There's a 1 over r squared, the radius coordinate here. But if you look at this basis, some basis vectors have different lengths depending on where you are on your manifold. So here the manifold is just a flat plane, so also R2 and R3 and so on are manifolds. Of course, just very simple ones. But if you switch to an orthonormal basis, which is often very useful and common, then this multiplier here also changes from 1 over r squared to 1 over r. So it really does not only depend on the coordinate system, but on the actual choice of coordinate vectors that you use. If you look at such an equation and you don't know what the convention is for the coordinate vectors, you basically cannot pass this equation correctly. So you don't know if 1 over r squared is correct or 1 over r is correct. Both are correct in their correct context, but if you mix up the context, it's just incorrect. So it's much easier if you always have this, because this equation is always the correct one, and you can just directly convert to the other one if you really need it, which then works with the metric, or in this case, it's the inverse of the metric, because it goes in this direction instead of the other direction. Okay, so if you look at the velocity gradient tensor, nabla v, that's very, very commonly used in flow visualization, for example, to detect features in flow, such as vortices and so on. This is often written as a Jacobian J, so a Jacobian matrix of an arrangement of partial derivatives of the vector components derived in all the different spatial directions. The problem is here, this is correct, but only if you use Cartesian or affine coordinates. If you use another coordinate system, it's immediately incorrect. What is correct in every case is what is called this covariant derivative. So if you just use the recipe for the covariant derivative and substitute this matrix J by the corresponding nabla V, where the nabla really has the meaning now not of partial differentials, but of actual the covariant derivative, then you get this matrix here. You can write it in components. So in these components, there's not much difference, just that these components are differently computed than these components. And the general recipe just has kind of correction terms, which are connection coefficients or Christoffel symbols in this case. So you can see that these symbols here, are these kind of coefficients, they use the partial derivatives, but it's not only partial derivatives. If you have Cartesian and affine coordinates, this here goes to 0, so then this part falls out, so you might never notice that it's even there. But if you have general coordinates, this part is always there, and then some of these symbols are non-zero. And then, of course, if you use just the partial derivative, everything becomes incorrect. So we'll look at that in more detail later. So this was like a quick preview, and so now we'll start with the basics of mainly manifolds and coordinate systems on manifolds. So you might also think that a coordinate system is very clear, which I think most people can easily work with coordinate systems. But I think it's actually for tensor calculus to get everything right, it's really important to understand every specific detail of a coordinate system, or like a coordinate chart on a sphere, for example, because otherwise from these simple basics there can be lots of mistakes later on that are usually correct as long as you use Cartesian coordinates and simple flat spaces, but that become incorrect quickly when you use a little bit of a more complicated setting. And this more complicated setting can just be using polar coordinates, for example. Then immediately some mistakes can crop in. So in principle, what's a smooth manifold? So it's like it's at every point is a space where at every point of the space you have an n-dimensional neighborhood. Basically, it's homeomorphic to an n-dimensional disk. That would be a topological manifold, but then you add a smooth structure that allows you to do derivatives. And then later we'll see on top of that we add this Riemannian structure. But roughly speaking, you can just say at every point on a manifold, such as this sphere here, or also just flat space, R2, you have at every point a tangent space, which is a linear space. So you can see here that the sphere is not a linear space. So it's not a linear manifold, but at every point it has a tangent space, and the tangent space, by definition, is a vector space. So it's a linear space. So what you want to do is basically you want to compute derivatives for many applications, and in order to do that, you cannot just compute directly on a manifold, so you try to put a coordinate chart on a manifold, and then do computations in these coordinate charts. But as you can see here, even on the sphere, in general, you need at least 2 coordinate charts, so you need to do a transition between 2 coordinate charts, and in a transition region, it's kind of clear that you will have 2 coordinates, so basically you have to switch from one coordinate chart to another coordinate chart, which immediately, I guess, points to the fact that computations cannot depend on what coordinate chart you're using, because first, it's not physical to just use one coordinate chart. I mean, physical meaning should be independent of this purely computational choice. But also here you have 2 coordinate charts that are different, so if a result is only correct in one and not correct in the other one, it just doesn't match together. So basically, tensor calculus defines how all of these computations are fully geometric or physically, in some sense, independent of the coordinate chart to be able to handle all of these problems. But basically, that then allows you to transfer simple calculus in just Rn to any n-dimensional manifold, and it all will work correctly as long as some basic rules are basically obeyed. So it just means that at 2 points on a manifold, we can look at 2 example tangent spaces. Actually, in general, this is also an abstract tangent space. You don't necessarily have to draw it on the sphere. You can do many computations by ignoring like the geometric picture underneath, but of course, often you do have that, so you would draw the tangent space as a tangent plane, the typical tangent plane. And in the tangent plane, we have vectors. And for example, if you have a curve on a manifold, so the curve is then not flat. I mean, on a curved manifold, it cannot be flat. So basically, we take the tangent vector of the curve, and then the question would be, where does this tangent vector now live? And it does live in the tangent space at that point. So the vector is straight, so it's a linear object. It cannot be straight on the sphere. Where does it go? It goes into the tangent space because the tangent space is a linear space. So computationally, just I wanted to show this briefly, I said it before. So in the end, the question is like, how do you compute in some coordinates, but still being independent of whatever choice for coordinates you did? And also maybe do intrinsic computations. So a sphere is a 2-dimensional manifold, although you often think about it as embedded in 3-dimensional space, which is fine to some extent, but you can, if you treat it as a 2-dimensional manifold instead of a 3-dimensional manifold, of course you can compute everything with 2 components instead of 3. So let's look at coordinate systems from the ground up, let's say, which might seem, like I said before, too simple, and to some extent it is, but there are some gotchas that can easily put you off track, kind of. So if you look at a coordinate system like a Cartesian coordinate system, it's often represented as a collection of 2 basis vectors, I and j, or something like this, and the question would be, is the coordinate system just this collection of basis vectors? And well, if it's a flat space and the basis is the same at every point in the flat space, you can do that. But in general, you don't use these vectors directly, but you use what's called a coordinate function. So every coordinate is just a scalar function that's given, so there are no vectors yet. So basically here, even Cartesian coordinates would have the first coordinate function x, or x1, and the second coordinate function y, or x2. So these are not to the power of 2. This must just means x2. This comes from tensor notation, where basically equations become simpler if you just enumerate things instead of calling it x, y, and z. You call it x1, x2, x3, and so on. So you have these coordinate functions, but in the polar coordinate system, of course, they would look different. And in an n-dimensional manifold, you just need n coordinate functions. And then the question is, where do now the basis vectors come from? Well, they come from taking derivatives of these coordinate functions. So even the construct of these basis vectors that everybody is used to comes from taking a derivative of an underlying function. And in a general setting, that's quite important. So these derivatives are then often notated like this, denoted or something, denotation like this one here. But basically, you can get basis vectors, but the underlying important primitive is basically a scalar function for each coordinate. Then you can plot isolines of these functions and so on. So often you rename then I and j to ex and ey, or e1 and e2, but the simple thing in Cartesian coordinates is that at every point in the space, in the manifold, it's the same basis, but in general that also doesn't work. So if you think about the sphere, it cannot be the same basis at every point on the sphere because it's not a flat space. But even in the polar coordinate system, in the plane, so this is a flat space, but if you look here, these vectors here are differently rotated than these basis vectors, and this basis vector here is also longer than this one because it resides from a derivative of the coordinate function, and the angular function just varies faster depending on the radius. If the radius gets bigger, the angle varies faster. So that's why this basis vector is longer, because it's coming from a partial derivative. Of course, then you can normalize these vectors, but then basically you immediately go to something a little bit more complicated, where it's not a coordinate basis anymore. So you can transform, of course, the basis, but it depends on where does the original basis come from. But before we do that, let's look at the coordinate functions a little bit in more detail. So basically you can say there's a coordinate map phi, or whatever you want to call it, that takes any point on the manifold M to the n-dimensional coordinate space, right? So it's basically a mapping between the manifold. It doesn't have to be a flat Euclidean space, but you map it to a coordinate tuple for every point. So phi of x is the first coordinate of x and the second coordinate of x and so on, up to the nth coordinate of x. So in the polar coordinate system, that would be 2, like for the radial coordinate and the angular coordinate and so on. So sometimes, of course, you do write it like r and theta or something like this, but in many computations, you still just have an enumeration and then you match indices, because it's harder to match letters instead of just matching numerical indices. So coming back to these tangent spaces, basically we start first with coordinate charts. So there's one chart and another chart. So there's a fundamental reason why you cannot cover, topological reason basically, why you cannot cover the sphere with one coordinate chart without having some missing points. So at least you would have the North Pole missing or the South Pole missing or both missing and so on. So you need at least 2 charts, but each one of these charts is now such a coordinate function for the chart, and it just maps this 2-dimensional region to a 2-dimensional part of R2. And another coordinate function would map this region on the manifold to this part of R2. So what you now want to be able to do is you want to be able to compute here or be able to compute here, but everywhere it should do the correct thing, especially always in this overlap here where these charts overlap. And then at these positions you would also have tangent spaces. You can also, for computations, directly map from R2 here to R2 here, which is basically a transition map in this transition region. So you just take the inverse of this map and then you go along this map, which gives you this composite map and so on. So it looks notationally a bit complicated in the beginning, but if you get used to it, it's actually very, very simple. And it's very powerful. So this is just a summary of what I said before. So the important thing is really that you see you have to use multiple coordinate charts in the general setting. And that, of course, directly shows the output of your computation, the geometric output, like the direction that the vector is pointing into, and so on, cannot be dependent on just these numerical computations. It has to have an independent or invariant meaning. So you can compute in coordinate-free formulations, especially when you do like a derivation on paper or so. At some point, often, especially if you do if you write code, you have to compute in coordinates, but of course the meaning should be independent of these coordinates. So that's the important thing here. Another thing is then, of course, if you have coordinate functions on a manifold, you can look at curves through these coordinate functions, where you basically would have a coordinate curve for every coordinate, and you would say you fix all the coordinates except one, and then you just vary one chosen coordinate. Let's say you vary the x coordinate or you vary the y coordinate, and then you get the inverse map of the map that maps to the coordinate space. And then if you vary one coordinate here, like the parameter t for the curve, you would trace out these curves on the manifold, in this case the sphere. You can see weird discontinuities here is because there's multiple charts. So here you see like 4 charts or so, the whole sphere is covered with 6 charts. And so there's transitions. Of course, these transitions have to be handled. Basically, you take derivatives from the one coordinate system going to the other one, and you just have a linear transform that changes from one coordinate system to the other one. So why is this important? So well, let me go step back a bit. So as we talked about the functions, not the vectors, but then we need basis vectors in every tangent space. So where do they come from? Again, they come from derivatives of these functions. And basically the basis vectors, if it's a coordinate basis, so we'll see that there are also non-coordinate bases, which can be also confusing in the beginning. But the coordinate basis is the partial derivatives of these coordinate functions. So basically we had just this coordinate map or the inverse that gives the coordinate curve. If you take the derivative of this, in this case it's the partial derivative because we vary only one coordinate, we get a tangent vector. It's the tangent vector to the coordinate curve. So these vectors here, different notations, they all mean the same. This is very common in physics or mathematical physics, for example. The basis vector di that resides from taking a partial derivative of the coordinate functions, they span a basis at every tangent space. So for every tangent space, you can take this derivative, and then the derivative that you get is a vector. It is the tangent to the coordinate curve. Peter will show that in more detail later. And this is the vectors that you can compute with. But of course, if you go to one tangent space, you can do a change of basis, and you can change to a basis that's actually not the coordinate curve. How this is measured is what we'll see also later using the Lie bracket or the Lie derivative between vector fields. What's a bit hard to see in all of these notations, so you do this at every point on the manifold, so you get functions over the whole manifold. It looks like you get this only at one point maybe, but basically you get vector fields out. So these coordinate vectors at every point form vector fields over the whole manifold. And these vector fields, you can check if they commute, so we'll see in a bit what that means. And if they commute, if this location, so this Lie bracket, these weird brackets here that have 2 vector fields as input, produce another vector field as output. If this output vector field is 0, it means that these 2 vector fields commute. If they commute, this forms a coordinate basis. If they don't, it forms a non-coordinate basis. And in general, these vector fields don't have to commute. You would have to compute them such that you know they commute, or you have to check if they actually do commute. So that brings us to a little bit about non-coordinate frames. So a famous differential geometer who used it was Élie Cartan. So basically, on many manifolds, if you use an orthonormal frame, so you want to have an orthonormal basis, the orthonormal basis is often a non-coordinate frame. That's even true in polar coordinates that we saw already a little bit before, but we'll look at it in detail again. So you would have the basis vector fields over your manifold. If you compute the Lie bracket, it would not be 0, and that means it does not commute. But of course, having an orthonormal basis has many advantages. So either you use the non-orthonormal one, you have the advantage that it's a coordinate basis or frame, or you use the orthonormal form where you often would have the disadvantage that it's a non-coordinate frame. So both have advantages and disadvantages. So, I mean, this is all done in the general setting. For example, in general relativity, this is extremely important. But I think it's interesting that it even comes up in extremely simple settings that most of us know, but sometimes maybe you miss some important details, like polar coordinates just in the flat plane, right? It's more clear on the sphere that you cannot have the same basis at every point because the points lie on this curved manifold. But even if you're in flat space, if you have a coordinate basis, you have different bases at every point. In this case, the Lie bracket commutes. And if you just normalize these vectors, they don't commute anymore. And all of these problems come up even in the flat case just because you're using a non-Cartesian coordinate system or a non-affine coordinate system. This commutativity you can basically imagine as saying, well, I have more than one coordinate, and I first walk along an integral curve of the one coordinate. So I go, let's say, along the angular coordinate, like this, and then I go along the radial coordinate like this. And then the question would be, if I do that in one order or the other order, so I first go along the angular coordinate and then the radial or the other way around, do they actually arrive up at the same point? So this is what commutativity means. So you can change the order in which you start integrating, and then you arrive at the same point if this lead bracket is 0. But if it's a different basis, so this orthonormal one here at the bottom, then actually, let me step here, you do the same thing again, but you don't arrive at the same point. So if you think about this integration, this happens, so it does not arrive at the same point. Depending on the order, you arrive at a different point, so it's not commutative. But in the end, it's not about integration. In the beginning, it's about the derivative of that. So basically, you can measure that differentially. So you don't have to walk along a curve. So it's even at one point, infinitesimally, you can measure if this is commutative. And this is what this Lie bracket measures. But then if you start integrating, you will exactly get this problem that you don't end up at the same point. Okay, so this is also why it's a non-coordinate basis, because then basically depending on how you go, you would end up with different coordinates, and of course you cannot have different coordinates for the same point in the same coordinate system. Okay, this has also other applications. So there's a very nice paper here about integrating stream surfaces. So it's very common in diffusion tensor imaging to have a matrix that represents the diffusion tensor, and then you compute eigenvectors of this matrix. And then you hope that these eigenvectors span a two-dimensional surface, for example, like a stream surface. And then you have the same problem here. You need to check if these eigenvector fields actually form a surface. So if you start integrating, do you end up on different points and actually not on the same surface? And it's the same measurement as this integrability of coordinates. Basically, there's a very general theorem, it's called the Frobenius theorem, that measures integrability. So there's an integrability condition if a specific set of two vector fields in this case can be integrated together to form a 2D surface. It is not always given that this works. It only works if, again, this Lie bracket in some sense is 0. So in this case, you have to check if it's basically in the same tangent plane, so you have to check the normal component if it's 0. So these things can be integrable, they connect together through integration, or they can be non-integrable. And if you just get some vector fields, you don't know. So you really would have to check if they integrate together. That's a very subtle point, but an important point that I guess is often missed. So also this paper, for example, very nicely shows that previous stream surface computation papers of diffusion tensor imaging did not check for this problem, and some of these surfaces, of course, turned out to be non-integrable, so it basically is incorrect to integrate them like this. Okay, so for further considerations, we'll now go from the basis that we just looked at to what's called the dual basis. So basically the basis vectors form a vector space. The dual basis forms a dual vector space. But the dual basis is even more than vectors. It's not vectors, it's more functions. So these functions are called one-forms, or like an older name is covectors. It's linear functions that take vectors to scalars, but basically it is the function that takes a vector as an input. Sometimes you can write it like this. So this omega here would just be a symbol for a specific one form, and this is the ith one form. And what you can do, for example, is you can read off coordinates. So if you have a vector and you want to know the scalar components given some specific coordinate system, you can write these one forms for the coordinate system, and then applying this function to the vector would give you the corresponding coordinate component. If you, of course, put the basis vector in itself, it either gives you 1 if you read the nth component of the nth basis vector, or it gives you 0 if you read the component of another basis vector. So basically, for a general vector, you can just say these are functions that just read off components. The input is a geometric vector, and the output is the ith component function. It's the same for the gradient, just in a more general setting. So in the end, you always have kind of vectors and these one forms, and the vectors have purposes for the one thing, and the one forms have purposes for the other thing. The important thing is that these one forms are functions that have a scalar output, and they basically read off information of vectors, for example. So in the end, if it's a coordinate basis, you often write it like this. If you have a general basis where you haven't said, is it a coordinate basis or not, you can write it like this. So you have basis vectors that you write either like this or like this, and you have the corresponding dual basis, that's the one forms. So these would be the coordinate differentials. So these are vectors, these are one forms, and dxi would read off the ith component of a vector. If you're not sure if it's a coordinate basis, you could use this notation that I just used before with an omega. So omega I would be one specific one form, dxi is another one form, but this one form was actually computed by taking the exterior derivative of the scalar field. So I guess this is a bit confusing in the beginning. It sounds all very complicated. You have to take time to go through it a little bit, but afterward it's relatively easy, and it just makes a lot of computations easier if you just separate clearly into vectors and one forms and use them for the corresponding purposes. So if you look at that in two very simple examples in the flat space, so first with Cartesian coordinates and then affine coordinates, which is already a bit more complicated, and then Peter afterward will show it on the sphere. So we go back to the coordinate functions. So basically here for the Cartesian coordinate system, we will have the first coordinate function and the second coordinate function. These are now isolines of the coordinate function. So these are not the coordinate curves. It's kind of orthogonal concept, but not really. But these are isolines where the coordinate function, the first one is constant. So here the x coordinate is constant, and here the y coordinate is constant. And then you have the coordinate lines, right? So these ones go kind of vertically, and these ones go kind of horizontal. And these are the basis vectors. They are tangent to the coordinate curves, and these are the isolines. So that's a bit hard to draw, but in n-dimensional space, basically what you always have to think of is for coordinate functions, you hold one coordinate constant, and then you get basically n minus one dimensional level sets. So here it's two coordinates, so the n minus one dimensional level sets are 1D. So that's why it's these straight lines. But if you want to get the coordinate curves, you pick one coordinate and you hold all other coordinates constant. So it's basically also in that sense, it's kind of dual to one another. And so on a general manifold, you would have level sets as curves and so on, or as surfaces, as hypersurfaces. But if you want to visualize the basis one forms, they are linear constructs, it's basically linearization, then you would have linear level sets. So what does this now give us? So these are the level sets, these are the tangents to the coordinate curves. And then you can look at these basically, I mean, every one form corresponds kind of to a scalar function, and you can look at where does the scalar function vary and so on. And then you see, of course, the x coordinate varies in this direction, the y coordinate varies in this direction. Then you can ask things like, in which direction does it vary the fastest, and so on. If you switch now from Cartesian coordinates to affine coordinates, so you just basically tilt the basis a little bit, it's almost as simple, but there are already some complications that come in. So now, this would be the coordinate function, the first one, this would be the coordinate function, the second one. So here, basically, these tangent vectors are very similar to before, but these tangent vectors, they are already tilted. And now we already have the problem that basically this coordinate basis vector goes here, but the direction of strongest variation is in this direction. Because of the tilt, you have like two different directions. And this comes up in many cases where if you mix up the two concepts, you pick the wrong concept. So it's important to clearly separate the basis vectors from the basis one forms. You can, like I showed very briefly in the beginning, you can raise the one forms to the dual vector, but then you get kind of different basis vectors. So here, these two vectors are the basis vector x and y, but this is the co-basis, basically the dual basis. So this we would write as e sub x, and this you write as e superscript x. So then you have like two sets of vectors around that don't point in the same direction, which can be very confusing. But if you don't do two sets of vectors, but one set is a set of vectors and the other one is a set of one forms, it's much easier to keep them apart. Okay? So you can see, I guess, if you look at even simple affine coordinates, if you want to kind of do it in the general setting and you want to do it really correctly, it already is surprisingly complicated. So it takes some time getting used to this. So if you want to look at the one forms, as Peter will show in a hopefully easier to understand example later, with interactive, interactively moving the point and looking at the one form visualization. So, but basically a one form is really more like a scalar field in some sense. It's not a scalar field, but you visualize it like the scalar field and isolines of a scalar field. That's often called a stack, especially in physics. So basically you have a direction in which it varies the fastest, and then you have the isoline spacing here. So this is a visualization of a one form. So it's much more kind of a spacing of isolines in this case than a vector. So this is a way how you can kind of visualize this dual space. Okay, so if it's confusing, I hope it will become much clearer when Peter shows more examples. So to conclude this part, before Peter takes over, I want to just briefly use this now to do the first meaningful thing, namely to define vector fields and manifolds. And also you might think that a vector field is clear anyway, it's just a set of components at every point. But then we kind of said we want to have computations that are independent of components, so we also cannot say a vector field is just a set of components. If you look at a vector field V like this, and you look at the components Vi, so this again is of course not to the power of I, it just means the ith component, we have to pair these components with a basis. So basically the components have no meaning by themselves, they need to be paired with the corresponding basis, and then often if you have a Cartesian basic, you just leave these basis vectors away, because I guess like you would say everybody knows them anyway. But in a general setting, of course, it's very important to realize that it has to be paired. So the components, the scalar components, have to be paired with the corresponding basis vectors in the correct way. So again, here you see this Einstein summation convention. It does just not mean 1 Vi times 1 Ei. It means a sum over all the i's, and then it's like V1 times E1 plus V2 times V2, and so on. But also, you need the basis vectors in every tangent space, but it also means you need basis vector fields over the whole manifold. And then if you think about the sphere, for example, there cannot be a single vector field that does not have a critical point or a zero anywhere on the manifold. And the sphere is like a topological reason. It's a well-known theorem, sometimes called the Harry-Bole theorem. But a basis, of course, cannot have zero vectors in it. So you could immediately see that basically you cannot cover the whole sphere with one set of basis vector fields, because at some point it will have a zero, and at that point it would not be linearly independent, so it cannot form a basis at that point. So basically these things you can only do in a specific coordinate chart. You cannot do it for the whole sphere even. So what do you do in general? In general, it's what's called the tangent bundle. So you basically take the manifold to a higher dimensional manifold, which is kind of a gluing together of the base manifold itself with all of its tangent spaces. So if there's the sphere would be two-dimensional, the vectors are also two-dimensional, so in the end this tangent bundle that puts both together is four-dimensional, 2 plus 2. And then you say a vector field is just a function that takes any point on the manifold M to this higher dimensional manifold Tm, that's the tangent bundle, that includes now all the tangent spaces. So it has all the tangent spaces of all of the points inside of it, and then the manifold point X is mapped to its corresponding vector, but this vector is now kind of like a point in this manifold. So you basically, you raise this manifold notion to a higher dimension, and so you have like a point-to-point mapping, a point from this manifold to a point on this manifold. The meaning here is vectors, but it's basically points. And now if you want to expand it in coordinates, you can do that, but then you need the basis vector fields, and you can compute the components also only with respect to these basis vector fields, and you can only do it in one coordinate chart, but not necessarily for the whole manifold. So this is a global construct without coordinates that works always, and this is like an intermediate construct for computation just in one specific coordinate chart. Of course, if you're in R2 or R3, you can't just cover the whole manifold with one coordinate chart, so you would not have to notice this difference. But even on a sphere, if you don't want to have weird problems like North Pole and South Pole and so on, then even on the sphere, you have to cover the whole sphere with this construction. Graphically looking at this, for a 1D manifold down here, this is just an illustration. So let's say the manifold is 1D, then the tangent bundle is a two-dimensional manifold, so 1 plus 1. And kind of like these straight lines are supposed to now show the one-dimensional tangent spaces, but this is a manifold kind of covering all of these one-dimensional tangent spaces. So the vector field is just like this again, and it takes every point down here and maps it to the corresponding point up here. And this point-to-point correspondence between these two manifolds, this is now what's defining the vector field. And so this is one tangent space at one point x, so the whole bundle is Tm, one specific tangent space is T sub xm at the point x. And so you have the mapping from the point x to the point v of x. And then because you could have a different vector, of course, at every point, this curve here, that's the vector field, which is in this setting called a section of the tangent bundle. So it's like a curve that goes kind of through all of these tangent spaces, and the intersection at every tangent space is a particular point, which is the vector of the vector field at that point. And then you can take this to general tensor bundles. So a vector bundle would just a very special, a section of a vector bundle that's a vector field is a special case, but we can do the same construction for an arbitrary order tensor field. Okay, so for example, the metric tensor field, right? So the metric tensor field would be kind of visualized in a very similar way. And so you can do very general constructions that always work, and only for computational purposes, you just go to coordinates whenever you need them. All right, so this concludes this first very basic, hopefully not too confusing part, but now Peter will show you more, and especially also more illustrations of the same concepts.
All right, thank you, Marcus. Right, so brief switch of computer. All right, so Okay, so the rest of this session, the goal is now to also see what tensors are and tensor fields, and we will do this by examples. So in the end, we want to arrive here on the right side, and we want to look at a very specific example, the metric tensor, which is like the arguably most important object in this tutorial, because this turns our topological manifold into a Riemannian manifold. And in order to arrive there, I will do examples for the specific two-sphere here. And I will first have to cover one forms again and show you examples of a one form, that hopefully this gets a bit more intuitive what they are and how they exactly look in this simple example. And even I will now again review vectors and vector fields on the two-sphere to have like this one example that guides you through all the way until we arrive at this metric tensor. Okay, so Marcus already presented all of this, but I now draw this picture on the two-sphere. So we have the sphere, and here we have a very specific choice of charts. So this is, again, just for this one example. So we just arbitrarily kind of chose these 6 charts, where we can see this here, how the sphere could like explode, or we could imagine it as exploding into these 6 charts. And they overlap, and we can put them together to this sphere. This is called an embedding in 3D. This is how we typically would think intuitively of a sphere, but it's just a specific choice of an embedding that we can visualize this here in 3D. Marcus was talking about these coordinate functions. They are scalar functions that are defined on the chart, so we can look at them here in the charts. So this would be like the first coordinate function, for example, the second coordinate function, and we can think of them really as scalar functions in these charts. And we can again put them back on the spheres. This, again, 1 and 2. These discontinuities, they are not artifacts or anything. This is just a necessity because we have multiple charts and there's kind of a jump between them. That's why we have these overlapping regions where both of them are defined. So if we need to transition between charts, then we can do that in these overlap regions. There's this, the coordinate curve. So once we have a specific choice of charts, the rest kind of follows. There's like a recipe what we can do step by step that follows from this choice of charts. And the first we have to do here, or can do here, are these coordinate curves. So here we see isolines of the first coordinate function and isoline of the second coordinate function. And these are really curves in these coordinate functions. I can also like superimpose them here. I mean, it's just for illustration that we have 2 different ones here, and we can just look at them superimposed. And that makes sense because we want to now look at the tangent spaces and how they are constructed on the sphere. So here, if we look at these specific charts and we look at the isolines here in the charts, then we can see that they're like nicely orthogonal. But that's again, it's because of the choice of the charts we do here. It kind of makes it simpler. When we now look at tangent spaces, then we have to remember that at every point on the sphere or on the manifold, we have a tangent space. And this is where the vectors live. So the vectors are the elements of the tangent spaces. I think I messed up my video. No, it's here. So when we kind of move now over the sphere, at each point we have to think of this space, this linear space that is attached to it. And we can look at these two vectors here that are the chart-induced basis vectors. So we can kind of think of, okay, there's like two basis vectors everywhere at every point for each tangent space. We have basis vectors, and again, we're making a choice. So there's like, we could use different kinds of basis vectors, but here we choose them such that they are always the tangents to the coordinate curves. That's why we have this visualization here of the coordinate curves, and then we kind of see as we walk along. Okay, the plan was to replay this video, but I lost my mouse. Oh, there it is. Yeah, it's not replay. Okay, so if you followed, then you could see that like when I drag this point between the different tangent spaces, that's the basis vector here, the chart-induced basis vectors, they always stay tangent to the curves. Okay, so this is like this simple example that we can now hopefully a bit better imagine how we construct from a choice of charts, of coordinates, how we construct these tangent vector spaces on the sphere. Right, and this is already very relevant in practice. So if you look at data sets that are, say, velocity, for example, wind data on the Earth, then what you would be given at each sample point is what you think of as a vector, but you would be given two numbers. And these two numbers, they're really the components that need to be referred to a basis, to a tangent vector basis at each point. And these are different bases at each point. So we somehow need the information how we construct this basis. And typically this would be for, say, one file format. You would have a convention that tells you for this kind of data sets, we use this kind of charts, and then the rest follows. You can you can construct the chart-induced basis, and you can refer these two numbers, the vector components, to actual vectors by just summing up the basis vectors times the components. All right, so now let's look at one-forms, and Markus has already started explaining them, and they're arguably a bit harder to grasp because they're kind of more unusual and less known, and they're very similar to vectors. In fact, they are vectors, they're co-vectors, they're also elements of a vector space, of the dual vector space, but we try to visualize them quite differently from vectors, and try to learn to think about them differently as vectors because they behave different as vectors. And they're very important, and it's easy to mix them up, the vectors and the co-vectors or the one-forms. So we try, at least with our visualization, to like make clear that they are different objects and that we can build like this intuition for them. Again, they are like vectors, they are coordinate independent objects, so they have a meaning that is not just fixed by the coordinate system, but we can visualize them independent of coordinate systems. And we will look at one specific example of a one-form, that's the gradient of a function. Something that's like kind of very well known, it's used all over in computer science, and often people still confuse it a bit and think it's like a vector, but it's not a vector, it's a one-form. Okay, so we can imagine one-forms as these scalar functions. They live in the one-form space, so like at each point of the manifold we would attach again such a space that coincides with the tangent vector space. At least we can think about it like this. It's have the same linear space. They also have a direction and a magnitude, and I put this here in quotation marks because I did not find a better term for it. So we can think of it as kind of a magnitude, but it's not really giving us anything like a length, because this will only be given later by the metric tensor. So anyways, they do have different metrics. So I can have like a one-form that has, for example, here, this one-form that goes like from -1 to 1, and it's as simple as this, as imagining it as this space. And now I can change, for example, the direction. It's very intuitive. Somehow we can very easily imagine that. But I can also change the magnitude by simply kind of changing the meaning of the color coding. So I could say, well, this is like double, right? So I just double that, and that's this magnitude that we mean here. Also, it's not a length, it's not a geometrical mean. Okay, so let's now see what it does. The one form, we have already seen that it eats a vector and then it makes a scalar. So it's a very simple object. As an input, we take a vector, and it's very intuitive how we would evaluate. We just read off this from the scalar field, basically. So all the vectors that would be pointing to this one line, that's an isoline of the scalar field, they would all evaluate to the same value. And we can do this for another example by like changing the direction. They would all vectors on this isoline would also evaluate to the same value, in this case 0.6. Okay, so now there's a better choice of visualization than this just color coding, because this is very dense, and also it's pretty hard to actually read off values. That's why it's quite common to visualize this one forms as stacks of isolines. And again, nothing has changed. Now I just chose to like leave away all the rest of the color coding and just draw isolines, which makes it easier to see the direction of it and also the magnitude. So for example, here we have the same example. We read off this vector, which evaluates to 0.8. And if I now change the magnitude, then the same vector would read off to double it. So here in this example, what I chose is that all these isolines are equidistantly spaced at 0.2. Pretty arbitrary choice, just because it looks nice. I could, of course, change that, but I don't change that for the rest of the presentation. So all my isolines are always spaced with 0.2, and when we do examples how to evaluate one forms, it will always be 0.2. So if we go and count here, we would count 8 isolines from the center, and that would evaluate to 1.6. All right, so let's look at this now in a visualization again on the 2-sphere. So again, on each point of the manifold, on the 2-sphere, we have this space, the one-form space. So here again, I draw the tangent space, and now I can have a one-form space. And exactly like the vector space basis vectors that are induced by a choice of charts, the charts also induce the dual space, a basis for the dual space. So we have basis one forms. And what I'm visualizing here is the first basis one form. We can easily see that the vector would read off the 5th isoline, so that it evaluates to 1. And that's the definition of the dual basis of the one form. I have the same, of course, for the second basis one form. Sorry. Sometimes the animations are not playing. Okay, so this would be the second basis one form. And now, of course, because this is a linear space, it's a vector space, we can do linear combinations of these one forms, just like with the vectors. So here I show an example. I mean, this you don't have to worry about this tiny user interface here, but basically I can like now input components and make linear combinations of one forms and vectors. So all I will do here now is basically show different examples of one forms and of vectors in this vector space. So by changing the components, I can like construct from the basis one forms, I can construct all possible one forms in this one form space at this one point. So I can increase the magnitude, which makes the isolines go closer to each other and evaluate vectors to higher numbers. I think I also have an example in a second. Right, so here's just examples of how changing the one forms would result in different evaluations of example vectors that we have here. So for example, this basis vector would evaluate to 0.2. But of course, this works not for basis vectors only, but for any vector. So we can do a linear combination of the basis vectors and then evaluate in this space any vector with any one form. Okay, so this is this construction of the basis, of the chart-induced basis vectors and the chart-induced one-forms. And now we will look at the first real example of a one-form, where like a one-form becomes useful, and that's the differential one-form called the gradient of a function. So we have a function on the manifold that's now visualized here. It's this color coding, like blue low values and red high values. It's just an arbitrary choice. It's just an example function, right? The only thing we need to know about it is it has different values at different points on the manifold. And now we can construct the one form, where we know this one form, the gradient one form, it needs at each point, it needs to be able to eat a vector and give us a scalar. So how do we do this? Well, it can only be a linear combination of the basis one forms. So here, this, it's very annoying that my mouse, I was using the wrong mouse. That explains a lot. This is better. So here we see these are the basis one forms, this dx here. The x is a scalar function, it's the coordinate function. The dx is the basis one form. The dy is the second basis one form. So if the gradient of a function, of the function f, is also a one form, and it can only be a linear combination of these two basis one forms. Again, it's defined at every point of the manifold, but of course it's different at every point of the manifold. So the question is, what are the scalars? And by the definition of the gradient of a function, this is just the partial derivatives of the function in the two directions. Okay, and now what we can do is we can like look around at like how this changes over the manifold with this specific example of this function. So first of all, the meaning of this gradient is a directional derivative of the scalar function in the direction of a vector. So I draw now here a yellow vector that is also, it's a linear combination of the base vectors. So we are now here at okay, we're now, I guess my mouse, I shouldn't use my mouse too much. Okay, so like at different points on the manifold, we see different one forms here. And of course then different vectors that are the directional derivatives of the scalar function can be evaluated. So here, for example, this vector here, the yellow vector, that coincides with the zero isoline would, of course, evaluate to zero, because here the function in this direction doesn't change. Yeah, sorry, I missed one important animation here. I'll try to replay that. No, okay, not working. I mean, the point was just to show like that this one form field, or this differential of one form, is just different at any point of the manifold, but somehow the animation is not working. Okay, so I don't know if you have any time left, but we are now arriving at the metric tensor, which was the goal of this session here. And for this, of course, we first need to say something about tensors, and Marcus already said that. So a tensor is again defined pointwise on the manifold, just like the one forms and the vectors. And we can again classify them, or we can classify them according to the type. So there's different types of tensors, and they are different by the number of arguments they take. Tensors can take one forms as inputs and vectors as inputs, and they also produce a scalar. So it's these functions that take n one forms and m vectors and give us one scalar value. And they're very useful because there's many different kinds of tensors that we can use for different purposes in physics. So the classification of the tensors would be by their rank or by their type, and this is like an n-m tensor. So it takes n one-form arguments and m vector arguments. The gradient of a function is such an example. It's a one form, and therefore it's also a tensor. It's a 0, 1 order tensor, or 0, 1 type tensor. So it takes 0, 1 forms as input and 1 vector as input, and evaluates to a scalar, which is the directional derivative in the direction of the vector. So now the metric tensor, it takes us from topological manifolds to geometric manifolds. So for the sphere, for example, here is like 3 different kinds of topological spheres, and the only difference is their metric. So we have, again, a choice on the manifold to make, that is the metric, and by choosing the metric, we get different geometries. So the metric is all about measuring lengths, measuring angles, and we kind of endow it as an additional structure to our manifold. It is a tensor field, so we have a 0-2 tensor, meaning that it eats 2 vectors and gives us a scalar. And the meaning of it is what we know as the inner product. And this inner product basically defines the whole geometry of the space. So what does the inner product do? Marcus showed that in the very beginning. So we can take this tensor, the G, that takes 2 arguments, V and W, and then the geometric meaning of this inner product is the product of the length. Now it's really a length of the vectors with the cosine of the angle between the 2 vectors. And that's obviously very useful because, well, we can now use this to evaluate the length of a vector by just putting the vector in both arguments, and then the metric will give us the squared length of this vector. And also we can use it to compute angles, or like the cosine of angle, by just putting 2 vectors in the slots of a metric and then dividing by the length of the 2 individual vectors. So that's obviously very useful, and it's the only way we can make geometrical sense on a manifold, on a Riemannian manifold in general. Okay, I'll try to visualize the metric tensor, or rather how a choice of metric can look like, and we will take the very intuitive metric that we are all used to, like on our sphere, that is like from the Euclidean embedding, we take basically the meaning of the Euclidean like Euclidean distances, and we take that and we will visualize that on the sphere now. And to visualize it, it's quite tricky because it's a 0-2 tensor, so there's like not very straightforward visualizations, but we will reuse the trick of converting one of the input vectors to a one form, and then we know how to visualize one forms that we have just practiced, and then we can kind of make sense of what this metric tensor looks like and how it evaluates and build some intuition maybe for it. So we'll just convert this 0-2 tensor to a 0-1 tensor by already plugging in one vector into the metric and leaving only one slot open. And we can do this again by actually we are using the metric to convert one of the vectors to a one form. So here the idea would now be that we kind of get an intuition for how to use this to evaluate the squared length and the cosine of an angle on the sphere. So we take this vector v, we plug it into the metric tensor, we convert it to a one form. Now we have this stack of isolines again, and we can use that to evaluate the second vector. So the second vector here is this w. And now we can kind of check for this first vector v, how the inner product would evaluate between these 2 vectors by just reading off from the one form again. So for instance, if I make the 2 vectors coincide with each other, then this would simply correspond to reading off this vector from the one form, and that would be the squared length. So the metric, when we kind of make the conversion into a one form, it takes care of it, converts it into this correct one form that will give me the squared length. And the other example is the cosine of the angle between the two vectors. So we change now, we take a different first vector v, we convert it again to the one form, this isoline stack. So let's choose something here that's a bit higher in magnitude. And then now we look at what the vector, the other vector that vector v evaluates to, and if I make it kind of perpendicular to it, then this would correspond to a notion of the cosine of the angle between it, because it evaluates to 0. So you can imagine the metric tensor kind of this, it is the inner product between two vectors, but you can imagine it a bit as converting the one vector into a one form and then evaluating the one form. I guess there's other options how to visualize it, but this is one choice that we made here. All right, and I think this concludes this session. We arrived finally at the metric tensor, which is kind of the goal for this session. And we are on the way, we have learned a lot about tangent planes, tangent bundles, differential one forms, the gradient of a scalar function, and many other concepts that are hopefully now more intuitive. I think that's it for now. We're going into the break. Do we have time? Oh, wow. That's unexpected. All right, any questions so far?
So in your sphere example, you showed where you were using like these 6 charts. You kind of mentioned you just picked up arbitrarily.
Yes.
So I guess there is some sort of guideline in picking the chart, because I think it would have an implication for implementation.
Yes,
So
exactly.
are there guidelines or?
Not really. There's different kinds of formats, for example, how data is stored, and they kind of tell you how they're stored. So they would typically use, say, a longitude-latitude chart, for example, and then either make sure they don't have data that's not covered with this chart, or they would have like 2 charts, like one on the bottom and one on the top, that also overlap via geometric projection. In the end, when you then go and you can convert this, of course, to other data, right? So you would take the input vector components and you can just convert it and map it into other charts. And this is what we have done here. The idea of having the 6 charts was like keeping it simple, keeping it illustrative, but yet having a efficient representation where we can, for example, compute streamlines in these 6 charts. So we can think of them like as very simple like textures, and we can even like in a fragment shader, for example, compute streamlines on these 6 charts. All right. If there are no more questions, then I guess we will see each other again after the break.